Levitating Balloons Lab, Group 2B. Introduction to Man-Eaters. Research question: how can an electric charge of two balloons be determined using the electric force? We use a gravitational constant to create an experiment using waves to determine the force of one charged balloon upon another. System schema: we have two balloons, one on top of each other vertically, and a scale on the bottom, putting them so close together to have an electric interaction. Experimental design: our design used a gravitational constant to measure the weight change of a balloon once electrical force was applied through the other balloon. To do this, we blew up two balloons of approximately the same size. One was attached to a small weight of 50 grams to keep it stable upon the scale. We labeled this as the free balloon. The other balloon was held above the free balloon, and we labeled it as a fixed balloon. The balloons were both charged through rubbing the balloons for 5 seconds upon different objects. 3 trials using a scarf and 3 trials using a person's hair. Once charged, the fixed balloon was quickly placed on the scale, and the free balloon was put 1 centimeter above. The number shown on the scale was then recorded. This number was then subtracted by the original weight of the balloon before force was put upon it. The resulting number was then multiplied by the gravitational constant to find the total force. The equation force equals Kc times 2q over r squared will allow us to solve for the total charge in each balloon. Physics evolved. Using electric force and Coulomb's law, we were able to solve for our charge. Electric force. Energy is scalar and force is a vector. In our system, there is energy and force acting between the two charged objects. Electric potential energy describes this interaction with U E equals Ke times Q times big Q times little q over RQ times Q. The relationship between force and potential energies is derivative. Assuming that our big Q and little q are equal, we will be able to treat this as a Kc times 2q equation. Unpacking Coulomb's law. This equation was used to help determine the electric forces are acting on each other in the system. Main ideas of Coulomb's law. Charges exert electric forces on each other, like charges repelling, opposite charges attracting. The forces each charge feel are proportional to the strength of the charges creating the force, and the charges feeling the force. The force gets weaker with the charge of the distance between the charges. Data and calculations. Mass of balloon times gravitational constant equals force. This force is then equal to Kc times 2q over r squared. Using the constant 8.99 times 10 to the 9th Newton meters squared over Coulomb squared, we can then insert that number in for Kc. Then, as we put the balloons 1 centimeter apart, our distance is 0.01 meters squared. Rearranging our formula to solve for Q, we have force times distance over 2 times Kc equals Q. Finding Q will give you the total charge of each balloon, and saying that Q equals the charge of both balloons, they will be the same. The number of electrons gained from rubbing the balloon is changed by the charge of the balloon divided by the charge of one electron. Charges determined. Using the previous equation, we were able to determine the charges of balloon 1 and balloon 2 in all the trials. Again, they should be the same because our assumption is they have the same charge and repel each other the same amount. The average charge of balloons on the scarf trials is 3.13 times 10 to the 9th. To divide the charge divided by the charge of one electron, the average amount of electrons moved from rubbing the balloon with a scarf is 8.23 times 10 to the negative 20th. The average charge of the balloon in the hair trials is 5.36 times 10 to the negative 8. Divided by the charge for one electron, the average amount of electrons moved is 3.3 times 10 to the negative 27th. Limitations and possible errors. We assumed that the charges on the balloons to be equal in our calculations, when in fact they may not be exactly equivalent. One balloon may have been charged more from human error while rubbing them on given objects. The balloons could have also lost charge through transport to the scale. We were unable to calculate those exact differences, which is why we assumed the charges were equal. The scale would not be able to detect changes in weight due to gain of charge, so we assumed that a charged balloon would weigh the exact same as an uncharged balloon. Conclusion. We were successfully able to transfer electrons by rubbing the scarf in the hair. The charge in each balloon was numerically small, but still enough to create gravitational mass that was calculable using Coulomb's law. However, by our calculations, the hair transferred fewer electrons than the scarf. The reason is possible due to the scarf having more contact with the balloon than the hair, or simply that some fabrics or materials have an intrinsic property to transfer more electrons than any other material.